We are a student team from the Rzeszów University of Technology. Our main passion is designing and building Mars rover analogs. These are special robotic platforms built to work on Earth, but they look and act just like the machines space agencies send to Mars. We use them to compete in international rover competitions, such as European Rover Challenge. Our team is divided into several sections to make our work more effective. The electronics group handles all the wiring and power. The mechanics group builds the physical body of the rover. The science group prepares tools for analyzing soil. And the IT group writes the software that makes the robot move. Finally, we have a marketing group that helps us share our work with the world and find partners to support our project. To move the rover, we use a custom desktop application. This application includes a live video feed from cameras mounted on the vehicle, allowing the operator to see exactly where the robot is going. The base station uses a Dell laptop connected to antennas to establish a connection with the rover. The main control application functions as a custom-built website that communicates with the rover via ROS2, which modularizes the system, speeds up setup times and simplifies the launch process. This solution enables multi-camera video streaming displayed across the laptop screen and an additional monitor, improving visibility and facilitating mission recording. To reduce signal interference around the antennas, the rover is controlled via an Xbox controller, connected to the laptop with a USB cable. The primary design goals for the communication and ground station system were to ensure adequate coverage, simplify operation, and maintain software expandability. Safety is incredibly important to us, especially when we showcase the rover. Because of this, our application includes a built-in speed limiter. We can easily cap the maximum speed of the vehicle. This feature guarantees that even when the rover moves through a crowded room full of people, it remains completely safe and poses no danger to anyone around. When building the electronics, we decided to use a modular design. Instead of making one giant complicated circuit, we broke the electrical system down into several smaller parts. We then placed each section inside its own sealed protective container. This approach gives us two major benefits. Easy maintenance. If something stops working, we do not need to rebuild the entire system. We can simply take out the broken module and swap it for a working one in just a few minutes. We can also add new modules if a specific task requires new feature. High protection. Space environments and even test fields on Earth are full of dust and moisture. Because our modules and the main body of the rover are tightly sealed, no dirt or water can get inside to damage the sensitive electronics. The drive section consists of 4 identical modules. Each module is equipped with a PCB holding an STM microcontroller with connectors that facilitate wiring to peripherals. The module includes a BLDC motor driver with a motor shaft position sensor, a stepper motor driver, and a MAX 3490 integrated circuit that manages the absolute encoder. The system communicates with the onboard computer via a CAN interface. The MOSFET board. This board houses the MOSFETs along with additional components. These transistors act as switches to activate individual circuits. The board also features transistors which use low voltage to control the MOSFET gates. Power is routed to XT60 connectors, each paired with an LED indicator that signals when the circuit is active. We operate using the MicroROS system. Because of this solution, our onboard computer communicates with the power section via the UART communication protocol. Additionally, we placed a large emergency stop button on the side of the vehicle. If anything goes wrong, anyone can press it to instantly shut down the whole system. The rover's autonomy architecture is based on ROS2 Humble running on a Geeko microcomputer, which handles system synchronization. Localization is managed by an extended Kalman filter that fuses data from 4 sources: wheel odometry, IMU reading, visual odometry, and RTK GPS. This configuration achieves a positioning accuracy of several dozen centimeters. For 3D mapping and spatial perception, the system uses an Intel RealSense D455F camera. The integrated IR pass filter mitigates solar glare, enabling accurate point cloud generation and depth data extraction in direct sunlight. This 3D data combined with a 360 LiDAR device is utilized for motion planning and obstacle avoidance. Our rover is equipped with 4 cameras that provide comprehensive situational awareness. 3 RunCam cameras are installed throughout the system. 2 mounted on the manipulator for precise operation and 1 positioned on the rover's frame to monitor its surroundings. Additionally, a DJI Osmo Action 4 camera mounted on the mast delivers a 360-degree view, giving operators enhanced visibility and control during missions. If needed, video is also transmitted through an analog vision system, delivering low-latency, real-time footage for precise remote operation. Our rover uses MikroTik Net Metal 5 communication modules operating on both 2.4 GHz and 5 GHz bands, providing fast and reliable data transmission. For longer range operation, we utilize a subtle 433 MHz radio link, ensuring stable communication over greater distance. The frame of our rover is built for difficult terrain. Drive system uses 4 independent wheels, and each one can turn 190 degrees, which gives the rover incredible agility. It can even turn around on a single spot without moving forwards or backward. At the front of the rover, we attached a robotic arm. This arm has 6 degrees of freedom, meaning it can move and bend in 6 different ways. Much like a human arm, controlled by our operator, it can perform highly precise tasks. It can pick up small tools, flip switches, move levers, and even press specific keys on a computer keyboard. We also use this arm to collect soil and ground samples from the field for our science laboratory to analyze. The manipulator consists of BLDC motors with integrated encoders, enabling precise controls of robotic arm. All motors operate via a CAN interface. The ARM control module uses 2 CAN bus controllers that transfer data to the main system through a USB interface. The gripper operates using a DC motor controlled by an H bridge. When designing our drone for the ERC competition, we focused on a completely proprietary enclosed housing. We manufacture it from fiberglass and resin, laminating them over 3D printed molds we prepared beforehand. Additionally, the multi-rotor frame features a positive arm dihedral, known as dihedral frame geometry. For many years, the legendary Rover team has been driven by a shared love for space exploration. Working on this project helps us expand our horizons, face new technical challenges, and experience a healthy dose of competition. For the past 2 years, we have been working hard to build a brand new rover. The upcoming European Rover Challenge is the perfect opportunity for us to show this new machine to the world. More importantly, it is a great chance for every member of our team to test their practical skills in a real-world scenario.